All right, this is for example 6.3. Let's continue to talk about the example problems using the response spectrum. So in the previous example problem, I'm going to show you the work that we went through. Okay, let me share my screen. Here we go. So this was example 6.2, right? We had this is kind of a water tank type the structure. So we have a large weight on top of the steel pipe column. So we were able to find out the K and M first based on the given information. So K was 0.211 kips per inch. So the mass, we ignored the mass of the steel pipe. So we based on the mass of the top portion, we were able to find out the fundamental frequency. From there, we got the fundamental period of the structure system, which is 1.59 seconds. And then the first one was what was the maximum peak deformation. So directly using the response spectrum, we got 5-inch displacement. And the second part of the question was the maximum bending stress. So using the sigma equation, sigma is equal to mc over I, and then c is the maximum y value, which is the half of the diameter, the outer diameter, so that we can figure out the spectral acceleration from the response spectrum multiplied by the mass. So that's going to be the inertia force at this level. Force times distance will come up with the bending moment. So using that moment, we got 46.5 KSI, which was the maximum stress at the outer surface of this steel pipe. So that was example 6.2. Now, example 6.3, it says that the stress computed in this previous example, 6.2, exceeded the allowable stress. So allowable stress might be the material property of the steel. And the designer decided to increase the size of the pipe to 8-inch nominal standard steel pipe. So initially it was 4.5-inch standard, the steel pipe. Now, because when we calculate the stress due to the earthquake, it was 46.5 KSI, which is exceeding the limit, allowable limit. So the designer said that is not strong enough, so he or she decided to increase the size of the steel pipe. So that's the starting point. I'm going to write down the information we have. So the nominal 8-inch nominal steel pipe is going to be used. So here are some properties. The outer diameter is going to be 8.625. Inner diameter, the I, will be equal to, what is this, 7.981. So that the corresponding thickness T is going to be 0.322. Okay, and kindly, this problem already calculated the moment of inertia based on these dimensions, which is 72.5 inches to the fourth. For your information, the earlier 4.5-inch pipe inertia, moment of inertia was 7.23. So in terms of the stiffness and the rigidity against the bending moment, this one is way higher than the previous example. So it might be a good choice based to reduce the stress in terms of the static point of view. Okay. So let's see how it goes. So again, because we changed the size of the pipe, that will affect to stiffness K, right? So K value was 3 EI over L cubic. L is still the same. Young's modulus of the steel is still the same, but the moment of inertia is changed from 7.23 to 72.5, almost 10 times. So when I calculate the stiffness, So 3 times 29,000 in KSI, now 72.5 for my moment of inertia, and then 12, converting into inches times 12 to the cube, it is going to be 2.112 kips per inch. So you can see that the stiffness of the changed pipe is way higher. So the earlier it was 0.211, now it's going to be 2.11 to almost 10 times of the stiffness. And that affects to our natural frequency, because omega n is equal to k over m with a square root sign. And again, we're going to ignore the weight of the steel pipe. So it doesn't affect to the mass term, but now the stiffness is changed from 0.2 to 2.112. So when I plug in those numbers, and this was 0.01347 from the previous calculation. So I got 12.52 radian per second. It was previously 3.958 radian per second. Now the natural frequency is changed to 12.52. And that affects to our period calculation, 2 pi over omega n. So it is going to be 0.502. Okay, so this is a big difference, right? So earlier with a 4.5 nominal diameter steel pipe, we got 1.59 second. Now, when we increase the size to 8-inch nominal steel pipe, period is now changed as well. Even though the stiffness is almost 10 times compared to the previous size of the pipe, now this period is changed from 1.59 second to 0.5 second. And we'll see how this change will affect to our calculation. So let me go back to the slide. Here we have a combined version of response spectrum. Again, we first figure out what is the period of the structure. That's the x-axis, and then go up to the intersection point with this chart. Going this way is going to be the maximum deformation. This way is going to be the maximum acceleration. This way is going to be the maximum velocity. So let's talk about the peak deformation. So I draw a straight line using this ruler tool. I didn't know about this before, but I just realized it. So using that ruler option, I drew 3 lines for the previous example problem. So this is the line with the 1.59 second. Now, so this is the intersection point. When we go this way, it will give us the maximum deformation, which was 5-inch, right, in the previous example problem. When we go the other way, then we'll get the maximum acceleration. That value was used to figure out the corresponding force, and force time distance, the height was giving us the moment, right? So this 5-inch maximum peak deformation and 0.2 g as a spectral acceleration value was used in the previous calculation. Now, period is changed from 1.59 second to 0.502 second, okay? So even though our structural system is stiffer, way stronger than before, but let's see how that seismic demand is going to be affected by that or not. So here is a straight line with 0.502 second. And as you can see, the corresponding value is now changed. So when we draw a straight line in this way, okay, the corresponding maximum value of deformation is, let's see, it is 2.7 inches. It's almost 2.7. So this is one tick for 1 inch, 2 inch, and this is the tick for 3 inch. So I would say 2.7. And when we come up with the acceleration value, it is around, this is 0.1, this is 1. it is around 1 G, which is a big difference from 0.2 G in the past. Okay, so let's just keep in mind and find out these changed value. And I'm going to go back to the document camera. So with 4.5-inch pipe, our D value was 5-inch. D is the spectral deformation, the maximum peak deformation due to the El Centro earthquake. So I'm going to use the SD. And SA was 0.2 in G. Now, we changed to 8-inch pipe. SD was 2.7 inches, and SA is now equal to 1.1 in G. Okay, so as you can see, we reduced the maximum peak deformation, which is good, right? So let's say here we have a structural system with the same ground motion. So let's say this is 4.5-inch pipe, this is 8-inch pipe. So with the same ground motion, El Centro ground motion, the maximum deformation at the top level due to the same ground motion, the first one is 5-inch, now the second one is 2.7-inch, which is better performance in terms of the maximum deformation. But what about the stress value? Okay, so we have a big increase from 0.2 G to 1.1 G, right? So we have a benefit to reduce the deformation, but let's talk about the maximum stress. To get the maximum stress again, we have to figure out this corresponding inertia force. And again, that W was, the mass was W over G, and now we have 1.1 in G. So GG canceled out, 1.1 times 5.2 in kips, right? So the corresponding force is 5.72 in kips. Let's compare to the previous calculation. With 4.5-inch pipe, the inertia force was only 1.04 kips. Now, due to the increase in terms of the spectral acceleration, almost 5 times, right? Exactly 5 times actually. And a little bit longer to 5.5 times. So anyway, so the corresponding force is now increased to 5.72 kips. Now, this times height will give us the moment. So the moment is going to be 5.72 kips times 12 in feet. So it is going to be equal to 68.64 kip feet. That is going to be the maximum moment. Now, compared to the moment before, it was 12.48. Now it is 68.64, which is really, really larger. Okay, how about sigma? So now stress max, sigma max is equal to mc over I. Now the moment of inertia is changed from 7.23 to 72.5. The maximum moment is also changed from 12.48 to 68.64, and the C value is also changed. The C value is going to be now the outer diameter divided by 2, so it's going to be around 4.3 inches. So when you plug it in those numbers, so it's going to be 68.64. I'm going to convert everything into kip and inches, multiply by 12, and then 8.625 over 2. Divided by moment of inertia at 72.5, I got 49 KSI. Look at this. So earlier we had 4.5-inch steel pipe. The corresponding peak deformation was 5-inch, and then maximum stress, the bending stress, was 46.5 KSI. The designer thought that is too much in terms of the stress, and that exceeds the allowable stress limit. So that's how the designer decided to change the size from 4.5-inch to 8-inch pipe. Now, going through the calculation, that change, selection of 8-inch pipe will reduce the maximum deformation from 5-inch to 2.7-inch, which is good. But in terms of the stress, right, it is even larger than before, from 46.5 KSI to 49 KSI, which is worse because our corresponding spectral acceleration value is almost 5 times than before. Okay, so look at the description in the solution. It says, using the 8-inch diameter pipe decreases deformation from 5-inch to 2.7-inch. However, contrary to the designer's objective, the bending stress increases slightly. So this example points out an important difference between the responsive structure to earthquake excitation and to a fixed value of the static force. So it shows us the difference, big difference, and very important point between the static analysis and dynamic analysis. The earthquake excitation is a dynamic analysis, and it is depending on the period of the structure, while the static analysis is not depending on the period of the structure. In the later case, which is the static analysis, the stress would decrease, obviously, by increasing the member size, because when you have a stronger material or the stiffened material, that will decrease this, the response. In the case of earthquake excitation, the increase in pipe diameter shortened the natural vibration period from 1.59 second to 0.5 second, which for this response spectrum has the effect of increasing the equivalent static force F, right? Whether the bending stress decreases or increases by increasing the pipe diameter depends on the increase in section modulus I over C, and the increase or decrease in the force F depending on the response spectrum. So the conclusion here is that as a designer, you have to keep in mind that this earthquake engineering and the seismic design steps analysis, you have to keep in mind the changes in the period. Whenever you change the size or the material property, even the weight, because weight is going to be directly affects to your mass, and material properties and the size of dimensions will be directly affects to your stiffness calculation. So stiffness and mass will affect to your fundamental frequency, which is the inverse relationship with the fundamental period. And that fundamental period will directly affect to your seismic demand through the spectral acceleration. So that's the lesson. And this is the last video of this week. So enjoy to learn about this topic. I'm going to post one more entertainment package problem for this week based on this learning. So you can check it out from the Blackboard. All right, thank you. Bye. Come on.